might want to leave a little bit of space on top because the headline will follow later. But let's assume we have a reaction, whatever this reaction is. Let's say, for example, we have a compound M. And this compound M is used up. And I like to illustrate it just with an arrow like that. So at the beginning we have lots of M, and this M then is used. Okay? You can probably imagine that. And what we want to find out is how much M do we have at certain times. And to illustrate that to you, I have prepared a little experiment, which I absolutely love in this context. And let's say I have Maltesers here. Have you had lunch? I didn't. I've got Maltesers here. Let's say, for sake of argument, I've got 100 Maltesers. And I say that I can eat 10 Maltesers every 2 minutes. Right? 10 Maltesers every 2 minutes. Huh? So I start with 100, and I eat. So my initial concentration of Maltesers, that's why the M, it could also be molarity. My initial concentration of Maltesers is 100. And my claim is I eat 10 Maltesers per 2 minutes. I want to know how many Maltesers are left. How many Maltesers are left after 6 minutes? How many Maltesers are left after 6 minutes? Huh? How many are left after 6 minutes? 70. 70. Who said that? You're welcome. 70. Exactly. How did you do that?
It's 10 per 2 minutes, so 2 times 3 is 6, so you just multiply 10 times 3, and you get 30, and you subtract from 100, so you're up to 70.
Pretty much, yeah. So what you could do is you can say, I start with 100. After 2 minutes, I've got 10 less, so I've got 90. So that's 2 minutes. After another 2 minutes, another 10 are gone, so I've got 80. And after another 2 minutes, another 10 are gone, so I've got 70 left. Absolutely right. Yeah? So that is basically how you would deal with a situation like that. Now we can write that in mathematical terms. And that is where it gets a little bit hairy. What we can say is we experience a change in the concentration of Maltesers. And a change in something is usually abbreviated with this delta sign. But in this case, we are looking at a very, very, very small change. in a very, very, very small time frame. And therefore, instead of this capital delta, we could write this as capital delta divided by capital T. This means in a long time period. But we don't have long time periods. 2 minutes is probably fairly short, but we can make this time period even shorter. I can say, how many Maltesers do I eat in 1 microsecond? So it would be written as dm divided by dt. And this d means, and I don't want you to write that in an exam, but this d means diddly squats. I don't know how you spell that, but it just means tiny, tiny difference. dm over dt. So that is the starting point. And we know by convention, and that's in one of the videos, if I consume something, like the Maltesers, if I consume something, then the whole thing gets a negative sign. So dm over dt equals negative, and that is because we have a consumption. So the Maltesers disappear. That's why it's negative. And then I told you I can eat 10 Maltesers per 2 minutes. So this is more or less a very constant thing. And I can do that till I'm sick. Or have a Malteser baby. Right? So, minus k. And this k stands for rate constant. People would usually argue, bless you, you spell constant with a C, but in this case you spell it with a K, A, because all these equations were developed last century by Germans, and they spell constant with a K. My apologies. And also C is already taken by the speed of light, and speed of light doesn't have anything to do here. So we have, for this particular reaction, we have this equation dm over dt equals minus k. So the change in Maltesers per time equals minus consumption k, a constant. So who gives a flying Malteser about this equation? Well, there's something you can really nicely do. And although Vivian has nicely demonstrated how you can calculate these things, it gets a little bit more complicated if you don't have these nice numbers. So 10 Malteser per 2 minutes, that's really nice number, but if the numbers are not so nice, then you have a little bit more problems. So you want to have probably some kind of equation that you can use for that. Okay, let me write this down first. dm over dt equals minus k. That was our starting equation. Now, those of you who have done a little bit of maths will recognize this first part, this left-hand side. What is this called? dm over dt. Loud? Say again? It's a differential equation, exactly. Whatever this on Earth means. Differential equation. And you deal with differential equations. How do you deal with differential equations, actually? You differentiate. What is the opposite of differential? Integration. Okay. Now, lots of folks here say, what the heck is he talking about? Don't worry about it, right? You do not need to know how you perform these different steps, unless you want to. And I will show you how it's done, but I'm not expecting that you remember that. We will end up with an equation at the end, which I want you to remember, however. So how do you deal with a differential equation like that? Well, the first thing is that you put the two d's on different sides of the equal sign. So you just simply multiply everything with dt. So you have on your left-hand side, you have dm equals minus k times dt. Okay? And now, as you rightly said, the opposite or the reverse operation of a d is integration. So what you do is you just integrate whatever this is, and we symbolize that with this sort of anorexic S, and integrate it here with this anorexic S, which actually stands for integral or summation in front of the dt. Now you have to find the stem function and God knows what. So don't stress too much about that. But actually, the function that you come up with for this, when you do the integration, you get the concentration of Maltesers, final. Let me write that down, final. That's your final concentration of Maltesers at a certain time point. Minus the concentration of Maltesers that you start with, that's the initial concentration, equals minus k times T final minus T initial. So M final minus M initial equals minus K times T final minus T initial. Right. Well, not terribly exciting, but what I want you to do is I want you to remember this equation. So we could, for example, calculate how many Maltesers have we got left after 6 minutes. So M final, that is what we are looking for. That is the number of Maltesers. M initial was 100 Maltesers. K was 10 minutes, 10 Maltesers per 2 minutes. T final was 6 minutes. And our initial time point, that is when we started the clock, that would be 0 minutes. Yeah? And if we did that, if we calculated that for M final, yeah, you can try out what this does, you would get 70 Maltesers. So this is a typical reaction. And I'm not telling you what this is called, this reaction, because we will do something very similar. But slightly different. But before I do that, what I want to show you is how we can graphically demonstrate this kind of reaction. Now what we can do is we can draw a graph where we have the concentration or number of Maltesers, and here we have time. Okay, so we have, let's say here we have 10 minutes, here we have 20 minutes, here we have 30 minutes, and so on. Let's say we start with 100 Maltesers. And we said I can eat 10 Maltesers per 2 minutes. How many Maltesers have I got left after 10 minutes? 50? You might wonder what he's going to do with that if somebody is sitting up there. So I encourage you to, the guys up there, to answer the next one. So you're absolutely right. We have 50 left. So that's about here. Oops. How many Maltesers have I got left after 20 minutes? 0. Who said that? You just had your Malteser. Okay, good. Okay. In this case, okay, after 20 minutes, we have no Maltesers left. We have a big tummy, and we probably feel incredibly sick. How many Maltesers do I have left after 30 minutes? Minus 50. Can I have minus 50 Maltesers? Sorry? Where did that come from? Who said that? Hands up. Okay, catch. Okay, if you ever want to be cricket, let's try it again. Okay, catch. Did you get it? But only second attempt, right? So becoming cricket captain is probably not the job for you. Maybe it is. I don't know. Maybe it is just my throwing. So we can't have negative Maltesers. It's not defined. So we would have to draw this like that here. Yeah? Now this is a typical concentration versus time curve. And what we get, if we look at it, if we look at the... I don't know. I just wanted to throw a Malteser at a student. If we look at the gradient of this whole thing, the gradient of this graph, this gradient here is actually minus, because the graph goes down, minus k. So when we look at this graph, we get our rate constant. So we have 100 Maltesers divided by 20 minutes, and that is 5 per minute or 10 per 2 minutes. Yeah? Happy with that? Okay, now I modify the job slightly for you. For that I need a piece of paper that I hopefully have taken with me, because I can't do that in my head. Okay, in the previous example, I said I start with 100 Maltesers and I can eat 10 per 2 minutes. That is what I said before. Now, my claim is I start with 100 Maltesers and I can eat 10% per 2 minutes. Do you see the difference? Yeah? Here I say 10 Maltesers, here I say 10%. How many Maltesers? Does everybody see this difference? Yeah? How many Maltesers do I have left after 6 minutes? Somebody said 70. 70%. 70 point? 73%? Actually, I don't know. I need to check my list. Who said 73? How did you do that? Uh-huh. So you did it step by step. So you said, okay, we start with 100, 2 minutes. Now 10% of 100 is 10. So how many have I got left? 90. So another 2 minutes. Now, I take 10% of what I've got left. So it's not 10, it's 9. Yeah? So I have 81. And next 2 minutes, 10%, 8.1. I can't have a 0.1 Malteser, I eat that usually. Minus 8. And that gives me 73. Yeah? Now you see, there is a difference between the first thing that I showed you, where we go really constant down, and this case. Actually, what we take away is changing. It's no longer a constant. Yeah? And if we were actually drawing this as a graph, what we would find, here's our Maltesers, here's time, let's say here's 100, we would no longer see a straight line. It would be something like that. It's a curve, obviously. Does that make sense? Okay, now, how are we going to write that as an equation? Again, we can start with our, what is called the general rate equation. So we can write dm over dt. That measures how fast the Maltesers disappear. That's our rate. That's our velocity. Is it a speed? Well, you have to go back to the videos that I posted, because I want you to know what is the difference between speed, velocity, and rate. Okay, we have dm over dt. That's our starting point. Equals. We have consumption, so what's the sign? Positive or negative? Negative. Must be negative. Why? Consumption. We still have a rate constant, and come back to that in a minute, minus k. But now, the really strange thing is that our rate depends how many Maltesers we have in each step. Yeah? So, and we write this as k times m. So it depends on how many Maltesers. When we start, we have 100. After 2 minutes, we have 90. Yes? So we don't have 100, we have 90, which we have to take into consideration. So now our rate equation, that is the general rate equation, our rate equation looks like minus k times m to the power of 1. Usually people don't write power of 1. K times m to the power of 1. Now some basic terminology. As I said, this guy here is the rate constant. This guy here, this 1, this exponent, is also called the rate order. So in this case, we would say this is the rate order of this particular reaction where m disappears. The rate order of this particular reaction is 1. So rate order is 1. Or we can also say it is a first order reaction. Does that make sense so far? Yeah? First order reaction. Now I showed you earlier, we have the reaction dm over dt, disappearance of Maltesers, minus k. That was our first case, where I pretended that I can eat 10 Maltesers per 2 minutes. Can we do the same thing? Can we define an order for that? Actually, we can. Because what we can do is we can actually write this as times concentration of Maltesers to the power of 0. Well done. Why can we write that? Exactly. Anything to the power of 0 is 1. So this thing here will disappear more or less. It becomes 1. Anything multiplied by 1 is the same thing. So what would you call this order? Or this reaction? It's a 0-order reaction. Zero-order reaction. So we have two cases. We have a 0-order and we have a first-order reaction. Now you could say, who gives, again, a flying Malteser? Okay. The difference between a 0-order reaction is, for the 0-order reaction, let me try to draw that. For a 0-order reaction, and we have our graph, Malteser time, we would see something like that. So the Maltesers disappear at a given constant. Yeah? For a first-order reaction, we draw exactly the same graph, Maltesers time, and we see that is a curve like that. Yeah? So the Maltesers disappear, but not at a constant rate. The rate is constantly, well, no, I should, oh, that's bad. The rate is permanently changing. Yes? So there's no constant in it. It is permanently changing. And that is a first-order reaction. That's very typical. Why do I mention that? Does it have any application? Indeed, it has, and a very important application. For example, the elimination of alcohol from the male body, follows pretty strictly a 0-order reaction. So you eliminate the alcohol. So for example, alcohol, elimination. In males, you follow pretty much a strict 0-order reaction, which means 1 pint, the alcohol in 1 pint of lager in about 2 hours. So, if you had 4 pints last night, it would take you 8 hours to eliminate the alcohol, if you're male. If you are female, it doesn't follow a 0-order reaction. I'm not saying anything. Let me put it this way, and I hope this will please you as well, Tiffany. It's not because you are superior. The the reaction order for females is more complex. So I would say, at least in this aspect, females are more complex than men. Yeah? Guys are zero order, straight line, no problem. Females, it depends on a lot of different things. Usually it is slower than men. Okay? So that's with alcohol. For a first order reaction, what are typical first order reactions? Very often we find that elimination of drugs, and I'm not necessarily talking about the elimination of the stuff that you smoke or, inject behind the bike shed. Not that you would. But medication, for example, drugs, very often follow a first order reaction. So very often drugs are eliminated by the kidney or by the liver and inactivated through a first order reaction. And of course, this is quite important for biomedical scientists, because you need to be aware of what this drug in particular does and how quickly it is eliminated from the body. Another thing that follows a very strict first order reaction is radioactivity. Anything that has something to do with radioactivity follows a first order reaction. So radioactivity, radioactive decay. And this does not at all depend on what type of radioactivity you have. It's always a first order reaction. Does it make sense? Yeah? Right. Now what I haven't shown you with this first order reaction, how we can translate that into a nice equation. Now I said to you, for a zero order reaction, we have the equation M final minus M initial equals minus K times T final minus T initial. That was the equation that I want you to remember. This guy here. And we can, of course, we can then rearrange this equation, and we can, for example, say how much of alcohol is left after, say, 3 hours. That's our alcohol final. You don't have to use M. You can call it whatever you want. Very often you will see it as abbreviated as A or B or God knows what. You can call it Pink Panther or, whatever you feel like it. Now, what is this equation for a first order reaction? Let's have a look. First order reaction. First order reaction, we have dm over dt equals minus k times m to the power of 1. Now what we do again is to deal with this differential equation, and again you don't need to remember that. I want to say that explicitly. You need to remember this equation this thing here. But how you get to the next one, don't worry, don't panic. What you do with that is you bring everything with d on different sides, and you bring everything with an m on one side. So what you have is 1 over m to the power of 1 dt equals minus k times dt. And as I said, don't worry about that. Oh, sorry, that was an m here. Confused you. Now you do the integration again. Integration. This part here, we've actually already encountered. That was for the zero order reaction. That's the same thing. So it has the same solution. It has minus k times T final minus T initial. And because I'm lazy, I just abbreviate that as TF and TI. But we haven't encountered the first part, the left-hand side. And unfortunately, I hate to say that to you, but this is a really tricky one, the solution to this integral, because it brings in an old friend. It brings in a log. Log we encountered, where? Where did we have logs? Huh? pH, thank you, exactly. My arse is ringing. Sorry about that. So in pH, and in pH we had the log to the basis of 10, right? Shut up. Now this time, nature is not as forgiving, because we not have a log to the basis of 10. We now have the natural log, which is the basis of 2.7181976. I can't remember the remaining 1,032,000 numbers. And we write this as ln m final minus ln of m initial. M final minus M initial. And it's ln. And the ln is to the basis of 2.718. Whew. Sorry? You can simplify it. You can absolutely simplify it. And how you simplify that, I'll show you next week. What I want you to do still is remember this equation. Okay? I know it's a lot to take in. It will be on YouTube if you want to have a look at it. And we are going to have quite a number of exercises about that, so that you really get comfortable with these two zero and first order reactions. Okay? We will do a second order as well. Yes, absolutely. Okay, have a good weekend. See you next week.